Okay, let me talk about this exercise 7.4.14 and remind you that we're talking about the dihedral group Dn, and Dn has this is the group of the symmetries of an n-gon. All right, so this is a proof question. Based on the results we've shown, prove that S composed R to the P must be a reflection for P between 0 and N. Remember, S is the reflection that leaves 1 fixed. And R is the smallest counterclockwise rotation that is a symmetry. And we've seen before that that's 360 divided by n degrees. All right, so I want to show that if I reflect, remember S compose R to the P means I take R to the P first and then reflect. So this means if I rotate P times, so that's going to be P times 360 over n, that rotation, and then I reflect, then I still get a reflection. Right. So it says based on results that we've shown, let's go back over the results that we've shown. And I've collated them here. First of all, we've proven that the dihedral group has 2n elements. Then we said that 2n elements may be listed in this way. And then we said that Dn consists of n distinct reflections in addition to n distinct rotations. Okay, so how can we put this information together to show that S composed R to the P must be a reflection? Well, let's do some counting here. We know there are 2n elements altogether. Some of them are here and some of them are here. These are the ones without S. These are the ones with S. And this one says that Dn contains n reflections in addition to n rotations. All right. Now, we've already identified the n rotations. These are all rotations. We know that because if you just keep on rotating, if you do a rotation followed by a rotation, it's still a rotation. So in fact, these must be the reflections. So since these are reflections, these are exactly the ones that that we have here. Okay, so we've shown it. We've shown that this must be a reflection because we've already used up the rotations and we need the reflections. So how would you write that down? You would say something like this. You could say by proposition 7.4.8. The 2n elements are, and I'm just repeating here, ID are Rn minus 1. Sorry, I don't want to put that. And then S to the composed R minus n to R minus 1. Those are the 2n elements. And then you say by proposition 7.4.113. Okay. Dn contains n rotations and n reflections. Okay. And then you can just say, since we know that the ID R all up to Rn minus 1 are all rotations, it follows that S composed R, S composed R to the n minus 1 must be reflections. Okay, so that's how you could write up this problem. Just circle that. This would be part A. That's an acceptable write-up for part A. All right, so let's look at part B. Again, we want to use our previous results. Okay, so using part A and other results we've shown that S composed R to the P composed S composed R to the P is the identity. Well, you want to look back and see what are the properties of reflections. In fact, if you look at 7.4.113, you'll see the property that you need. Then for part C, all you have to do is do this composition that's mentioned, composing on the left. So here I should say composing on the left by R to the n minus P minus composed S, show that R to the n minus P composed S equals S composed R to the P. So here it says, let me read this again. Using part B and composing on the left by S, R to the n minus P composed S, show the following. So what does this mean, composing on the left by R to the n minus P composed S? That means that you want to apply this on the left-hand side of both sides of this equation. Of course, you can't just do this on one side of the equation. You have to do it on both sides. So I'm going to take R to the n minus P composed S composed, this part, is equal to R to the n minus P composed S composed, the identity. All right, so you're going to apply this R to the n minus P composed S to both sides of this equation. Then you can use the associative property to move things around, and things will cancel, and you'll get the result that you want. Okay, that's it.